Okay, so start is that you're introduced to this, epsilon. Like, what the hell is epsilon? And you're told that it's a relation, which means that it's a predicate. Now, why a relation is a substitute name for predicates, I was at first very confused with. And there's also another thing, which is that a predicate of one variable is called a property, where a predicate of two variables is called a relation. And so I was asking myself, why is this? Like if I'm to say P of X, like for example, X is a human, how is that a property? But then later I came to realize that it's actually when you instantiate P of X and you give an actual value for X, that the object that you input gets given the property. Or when you have a predicate of two variables and you have two inputs, then that's why it's called a relationship, because when you instantiate it, the predicate becomes a proposition. And in logic, you're supposed to do everything in tautologies. A proof is just tautology after tautology after tautology. So if I'm introducing a predicate P of X, Y, and X and Y are actual things, then presumably that statement as a whole is a tautology, which means I have just said something like David is a human. So in other words, like a property of mine is that I'm a human, because like I've said that statement as a truth, like I've instantiated P of X. Whereas if you have a relationship, same thing happens. It's called a relationship because you have stated something, it's a truth, but it only becomes a relationship when you instantiate it. Although for some reason it's still called a relationship before that. Yeah, okay, yeah. So like, what do I mean by, well, that's the point, right? Like, why is it called a property? If I just have P of X and I say X is a human, like there is no property, like I have said nothing. But if we're talking in the world of proofs and I say Adar is a human, I have just given you the property that you are a human. And the only reason that's a property is because I've actually instantiated. I've replaced X with your name. But beforehand, it's still called a relation. I mean, a property for some reason. Maybe it shouldn't be.
Wait, hold up. So when you say it's like a property, like what is it a property of? Is it like P of X as a property of X, or like, yeah, like I don't really get that.
Yeah, and same thing with relationship. Like when you say R of XY is a relationship, it's like a relationship on what? Yeah, a relationship on what? And I think the idea is that you call it a relationship with the idea that later on, when you will replace X and Y with solid objects, and then you state, it's a statement, it becomes a truth, like, or a proposition, I'm sorry, or in this case, a tautology. It becomes something like Avnish is a human, Beforehand, it's X is a human, and then you're like, okay, what the hell is the property when you say X is a human? Like, you're not saying anything. But when I say Avnish is a human, then I have attached that property to you. True or not true? Exactly. Yeah. Like when you go to truth or not. Okay. And then next thing is with subsets and the equal sign. Okay. And I was confused with this because I think the subset is also a relationship. Like it's secretly defined as a relationship, which means that it's a predicate of two variables, which means that if X and Y are not solid objects, you have not said nothing. If I say that X is a subset of Y, I have said nothing. Like you actually have to replace X and Y with a solid object for it to become a truth or a falsehood. Beforehand, it's just like an abstract concept, like a relation, I guess, or a predicate of two variables. And same thing with the equal sign. If I say A is equal to B and I haven't said what A or B are, I've said nothing. Like I haven't contributed to a proof. It's only if I say, for example, the empty set is equal to the empty set is that it becomes valid. And then later on, we'll see that everything is actually the empty set, which is interesting. Cool. Okay, I think I've talked enough. Yeah, maybe I could get the last piece of the pie afterwards. But next up, we'll say, Avnish, do you want to get the epsilon relationship, the first axiom?
All right, let's see. So the epsilon relation states that X is, I don't know if I should write this, but basically like X epsilon Y, so X is an element of Y, is a proposition if and only if X and Y are both sets. So what we're secretly doing here, and it's kind of a sneaky way, is we're sort of telling you what we're sort of like explaining what X is and what epsilon is and what sets are without like giving a formal definition. So we're just like working with these axioms. So epsilon is a predicate, right? Like epsilon is a predicate of two variables or a relation, which means it becomes a proposition when you define X and Y, right?
Mhm.
So we don't know what X and Y are yet. We haven't defined them, but we know that they must be sets. So in that sense, we're kind of defining what a set is. And then in the lecture, what he goes on to do is he uses a counterexample to show like why we need this axiom, basically. And it's basically about like if there is a set, like if there exists a set that contains all the sets that do not contain themselves, is that thing a set? Okay, I haven't explained this correct in a good way. So if you assume that there exists some U that contains all the sets that do not contain themselves, then you ask, is that U a set? And we can prove that U cannot be a set. And I guess I can like try to play around with the iPad and see if I can.
Yeah, how about that as a test?
Write something with it. All right. Okay, so first I'll just write down what the thing is saying. So there exists a U such that for all Z, where Z is an element of U. So that implies that Z is not an element of itself. For every element, so we're assuming that there exists a set U such that for all of its elements, none of those elements are elements of themselves.
Yeah.
Basically, right? And how do we prove this? So we start with this, right? Is U an element of itself, right? We start with this. This is a proposition, right? Because it's a predicate of two variables. And since we've already defined U as basically like, well, we haven't called it a set yet, like a collection of sets that do not contain themselves. Since we've already defined it, it's either true or false. So if it's true,
yeah.
So if it's true, right? So if U is an element of U, then that basically goes in here, right? Because it's for all Z means like every element of U, right? And that includes U if U is an element of itself. But then that implies that U is not an element of itself because we just defined U as the set of all sets that do not contain themselves. So we created this contradiction here because if we say that U is an element of itself, well, that's a lie because it's supposed to be the set of all sets that do not contain themselves. So the other option is that this statement is false. And that could be a thing, right? Because propositions can be false. But if U is not an element of itself, sorry, 1 second. Yeah, so if U is not an element of itself, then it must be a part of itself, right? Because we've defined U as containing every set that does not contain itself, right? And if it contains all the sets that do not contain itself, then it's got to contain itself because we just said it doesn't contain itself. And it sounds like it sort of seems like we're throwing like a lot of words around. Does it contain itself? Does it not contain itself? But at the end of the day, there's no way for any of this to work, right? There's no way that U is an element of itself or it's or it's not an element of itself. So basically, we've just created a contradiction for both propositions, which means that U cannot be a set. So there is no set that contains all the sets that do not contain themselves. That's basically what we get out of this. So this kind of emphasized the importance of the epsilon relation. This is like sort of like an example of why we need it, I guess. Yeah.
Would you say the main reason that you need this first axiom is because of this Russell's paradox, or it's because you're finally allowed to turn predicates into propositions? To me, that's the main value, right? And this Russell's paradox is like a nice byproduct where it becomes illegal pretty much.
Yeah, I guess. So like we're basically the whole point of this is to like explain what the element symbol means and what sets are without actually defining them. So this counterexample sort of is like, yeah, a byproduct of that. At least that's my understanding of it.
Okay, cool.
I'm just gonna take a look at the chat.
Lana, do you want to ask your question?
Yeah, sorry. So I was just saying, like, so like the last axiom is like basically saying that like every set is not an element of itself, right? And like by this whole Russell's paradox thing, does that mean that there doesn't exist a set that contains like every single possible set? Because wouldn't that lead to Russell's paradox, since like it says that, oh, it contains Z if Z is not an element of Z. But
Wait,
like every set that we define cannot be an element of itself, right?
Can you re-explain? I lost you somewhere.
Okay, so you know the last axiom, right? It basically says that like for some set X, like X can't be an element of itself, right? So does that mean that there does not exist, like, I don't know, a universal set, a set that contains every single set, because then that would lead to Russell's paradox? Does that make sense? Right, because this is saying that all the elements of U are sets that don't contain themselves, but like every set by the last axiom cannot contain itself, right? So is there like, does that set of all sets not exist because of that?
By the last axiom, do you mean the axiom of foundation?
Yeah.
Oh.
That's the one that says it's illegal to make a set that contains itself, pretty much. So Teman, you have an answer? You want to hop in? Oh, and Avneesh, you want to stop sharing your screen?
Oh yeah, sure.
Okay, cool. Like on the iPad, yeah, cool.
So to show that there is no set that contains every single other set or a set of all sets, you have to use the axiom of foundation and the axiom of pair. And the way you go about doing so is the first thing you do is I'm going to give you any set A, right? Now, the axiom of pair says I can take two sets, A and B, and I can stuff them into another set like that, right? But what I can choose to do is I can take A, comma A. So the set of A and A. But what is that? That's just the set with A inside itself, right? Now, we are going to use the axiom of foundation. So the axiom of foundation we're going to apply to this set right here. This axiom says that as long as the set we're given is non-empty, then there exists an element in A. So there exists an A in A such that A union, A intersect A is equal to the null set. As in, there is something in A that is disjoint from the entire set itself. If I'm making sense here. Now, the issue is the only thing inside the set containing A is A. So therefore, the axiom of foundation says that A intersect A is equal to the null set. Therefore, if these two things are not contained in each other, then they cannot be equal. But if A intersect the set containing A is the null set, but the only thing in the set containing A is A, then A cannot be contained within itself. So therefore, A is not in A. Now, what this means is that if I take the set of all A such that A is not in A, if I take the set of all A such that A is not in A, but then for every set A is not in A, then I just took the set of all sets, which by Russell's paradox cannot exist.
Okay. I'm not sure I caught that.
Okay, so.
But wait, but I don't want to go over it again, just for the sake of going through the lesson. And next up is, let's say, Lana explaining the empty set axiom.
Okie doke. So, I mean, this one probably like the easiest one to understand. The one that I immediately got was just that there exists a set that doesn't contain anything. I don't know if anyone has any holes to poke in there.
How would you go about proving that there exists only one such set?
Okay, so this was one part that confused me, but basically it said that like, oh, assume you have like two sets X and Y, or he said like X and X prime that are both empty sets. You just want to show that X is equal to X prime, right? That means that there's only one empty set, right? And then basically the way he went about going the proof was like, so he said like for all Y, Y element X implies Y element in X prime. And then he said like you can do that and it'll always be true, which like that part, like I don't understand why it's like valid to do that, because like there are no elements in X. So what does that mean that that statement will always be true?
Okay, yeah, I found this interesting. He's basically taking advantage of ex falso quod libet, right? To say that because if X is empty, then it doesn't have anything inside it, right? So if you say Y is an element of X, that's false. And then he uses an implication arrow and then says, I can use like any proposition I want on the other side of that implication arrow. And the proposition he just so happens to want is Y is also an element of X prime. The thing about this though, it seems kind of like sus to use, like start with a false statement and then use that in your proof. Like that's something that I'm kind of like shaky on, right? Like,
it's a little counterintuitive. Yeah, but I mean, once you have that thing figured out, it basically like implies that X is a subset of X prime, and then you do the same thing to prove like X prime is a subset of X, and if they're both subsets of each other, they're equal.
Yeah. I feel like this is a common pattern. Like when you're coding, there's like coding patterns or whatever, or I don't know, programming patterns, whatever. In this way, it's like a proof pattern. Like whenever you want to prove that there's only one of something, what you can instead do is prove that if there were two abstract objects, those two abstract objects would be equal to each other, which means that there's only one. It seems to be like a sort of pattern. But yeah, cool. I think we've covered everything on the empty sets. Next one is pair relation. And let's see. I don't have a list of people here. Dixon, do you want to cover this one?
Sure. So pair relation, how I got it intuitively is like you just take two sets and basically you just jam them together and it's a-okay.
Okay, yeah. You're saying like you're expanding what is it? Like if you have a set here and a set here and you put them together, what the pair relationship tells you is this thing together is also a set.
Yeah, basically.
So question becomes, why are we expanding the definition of sets? Like, why is that useful?
So I think it's like you can use later on in other axioms, and then later when you have those 9 fundamental axioms, you can then build off like all mathematics. So yeah.
It's like you're expanding. I feel maybe the reason you're expanding the definition of what a set is because the only way to go from a predicate to a proposition is to instantiate the predicate with sets. And so of course you want more options. You're literally just giving yourself more options. Like if you start off very small with the world between propositions and predicates, and it's a very small world, every single one of these axioms just expands it and expands it. You have way more option to go around, I feel.
Yeah, I think this is just like the foundation of like building whatever set you want. Like it's just like the thing you need to say is true in order to build whatever set you want.
Yeah, because the first axiom tells you when you have the epsilon relationship, if X is a set and Y is a set, then the whole thing becomes a true or false statement. Yeah, and so yeah, you're just expanding what you can put in X and what you can put in Y using pair relation.
Have any of you come across something that kind of depends on the axiom of pairs in order to like be true?
How about this? If I was to tell you that the set containing X is equal to the set containing X comma X. Or no, I'm sorry, wait. If I tell you X is a set,
yep,
and I want to prove that parentheses X, close parentheses, is a set. So I'm telling you X is a set, and I want to prove that this is a set. I believe you need the pair axiom for this, the pair set axiom. And what you would do is you'd say something, you'd say like take an X, and then take another X, and pair them up together, and you get X comma X, which is defined as X.
Okay, I see.
Like that might be a case where you need the pair set axiom.
Yeah.
I feel like
I
it's
don't know.
kind of just sorry.
Yeah,
I
go
feel like
ahead.
it's kind of just giving us the ability to combine sets in a way, right? I guess like we want that to be a thing that you can do, and that's what the pair set axiom allows us to do. Especially because we use the pair set axiom to build up the axiom on union sets, right? So that's kind of like an important application of it.
Mhm.
Is it
Yeah, 'cause
true?
Oh,
How
yeah,
do you use it
for
to
union.
for the union axiom?
I believe it's
I feel
I
like
believe
all
it's-
axioms should be like, shouldn't all the axioms, be separate and like independent of each
mashed
other?
together. Yeah. Oh, well, like if I was to, for the union, it's a recursive definition, no? So you say something like, take
No,
the,
isn't that the naive definition of a union that's recursive? And then in like ZFC, it's not recursive, where you have like one X and then you define the union of all the elements of X to be the set containing all the elements of X.
yeah, no, that's the definition of union. Oh, I think it's if you're trying to build up a finite element set, which means a set with just whatever, like bam, 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 bam. Then you need the combination of the pair sets and the union set. And the procedure you would use is you'd take the first two elements, you'd pair them up together, and then you'd take this first element. Oh no, wait, okay, never mind, I'm lost.
Okay, I think we need to figure this out. Well, I guess like we can like write down like what he said, right? So if we say like let A and B be sets, then we're basically like giving ourselves the ability to start to take this, and then we basically define the union of this set,
Yeah,
to be
a set, yeah,
A and B,
yeah.
yeah.
Because that's in doubt. Like if I tell you A is a set and I ask you if this is a set, you can't be sure. Like naively, you're saying, oh yeah, of course it's a set. But if you're trying to be completely rigorous, like you're not sure if parentheses A is a set, or as Evanish just did, parentheses A comma B is a set. And so what these axioms tells you is it guarantees you, it tells you this thing is a set. And that's all it does. It has no other value.
It almost seems like the pair set axiom, which is kind of like what you just put in the chat, that's kind of what the pair set axiom is used for. It seems like that's more of like adding brackets and telling you that if you add brackets, you still have a set, and then union sort of like when you remove the brackets, it's still a set.
Yeah,
So that's kind of like what I'm thinking.
I don't know.
Like,
I still haven't
brackets.
I still haven't really internalized why you need the pair axiom for that. Like, for example, can we agree? Like, I'm not gonna say can we agree, but would it be fair to treat this as a set?
Ooh, yes. Because later on we see that one is defined as parentheses, parentheses.
You're saying it's defined as like this?
Yeah.
Yes. No. Oh, yes. But then, yeah, then you have the extra parentheses. So, yeah.
Yeah, by null, just meant like, but null is the thing in the, yeah.
Oh, in the middle. Okay, I see.
Yep.
Fair point.
So I guess this kind of like allows us to build mathematics, right? Because like we need to have sets containing sets, and that's kind of what the pair set axiom allows us to do. So like, like basically like David said, you can't be sure that adding brackets still maintains the fact that it's a set.
Mm-hmm. Like it feels like there's the first axiom, which allows you to turn predicates into propositions, and all of the other axioms just expand what a set is so that you can shove them into this first axiom to get a proposition. Because beforehand, if I'm trying to say something like parentheses A or element, whatever, like I'm trying to play with that object, I'm not allowed to even play with it unless I know it's a set. And so this axiom is telling me like, yes, that is a set. Yeah, and with union sets, I think that's what you do. Like you take A, you wrap it around. That's where the pair set axiom comes in. You take B, you wrap it around. Okay, maybe this is unnecessary. You take C, you wrap it around, and then you take the union of all of these guys or something. And then that's how you get A, comma, B, comma, C all in one set or something. But yeah.
I don't know if it's done that way.
Yeah,
at least
no, I feel
at
it's
least,
not. I feel like
at least I couldn't. It doesn't seem like it's done that way based on the definition given in the video.
Yeah. It's like, yeah.
But yeah, can we talk about the axiom of regularity or axiom of foundation?
You don't want to go through the rest first or not?
Sorry, whatever.
Okay, cool.
You guys
Yeah,
want.
it's the last one. Yeah, when we get to it, yeah.
Okay.
So next up is, we've already talked about the union set. Did we talk about everything in the union set? I guess one question that I might ask about the union set is why it's defined in terms of this big element on top, right? The definition of union set is something like, take a set, the elements of that set can be put together. It's like, why do you have this one big boy set at the top? And I think the answer to that is just because it ends up being, for recursion, I thought it's just a nice definition. Like, you have, like, all of your statements are about this one set at the top. So that way your definition is, a little bit more simple than it would be if you were talking about like a bunch of different ones and to just squash them together.
Also, did anyone like figure out the notation for like that kind of like notation for this axiom? Because like I'm trying to think about it. I have some ideas, but like, yeah, I don't know.
Adar, I think you got it. Do you want to
What did I
quickly
get?
dive into it? Like the formal definition for union in terms of the
Do you want
symbols.
me to write it down?
Yeah. Here, we'll try something
actually,
else.
yeah, maybe it would be nice to get you guys to double check it because I'm not. It seems right to me, but I'm not sure if it's fully right.
Okay, you guys can see the whiteboard, right? I believe everybody can write on this whiteboard.
Okay, so for all x, so basically the axiom or the axiom on union sets, like stated as like a sentence, is let x be a set, then there exists a set whose elements are precisely the elements of x. And so formally stated that this is what I got. So yeah, for all x, there exists some set which we will call U for union, where for all A.
Wait, Adar, I have a potential proposition. All right, okay, I didn't mean it that way, but do you want to write this down and then we talk about something else? And then when you have it fully written down, you can like circle stuff and point us to different elements. Because I think Lana here, you wrote something in the chat. Do you want to talk about that while Adar's writing stuff down?
Oh, I was just writing like the notation, like if you had x, what the union of x would be. So like if like x is like the pair of the set containing A and the set containing B, then the union would just be A and B because those are the elements of the set containing A and the set containing B.
If you were to replace the set containing B with the set containing B, comma C,
then it would just be A, B, C, because that's still, they're just taking the elements of that set and then like pushing it into this new set.
So essentially what happens when you're trying to form these bigger sets is first you use the pair set to make the set B, comma C.
Yeah.
And then you use the pair set to make the set parentheses A. And then you union them together. And now you have A, comma B, comma C. Now you take the set D, you wrap it around using the pair set. Now you take the union between these two. Now you have A, B, C, D. You take E, and then it's recursive. You just add until it becomes a really, really big set. So I guess that answers the question why you need the pair set. It's to do this kind of stuff.
Like it's just like the rigorous definition of like what is a set. Like you could just say, oh yeah, it's a set, but like why? Like you need to rigorous, I guess, like statement.
All right, Adar, you wrote it down. You want to explain stuff? Yeah, cool.
Yeah, so basically, if like the union definition is all it's really saying is if you have some set X which has as elements, I don't know, A, B, A, B, C, and like these have elements. All it's saying is that the union of A, B, and C is, or sorry, yeah, the union of the elements of X is just, or actually you might be saying the union of X. Yeah, so yeah, it's saying there exists a set which contains the elements of X. So there exists a set which contains these guys and these guys and these guys all together. And so how do you go about like formally stating that? Well, it's saying that this axiom applies for all sets. And so we start by saying for all sets X, there exists such a set.
Yeah.
So there exists a set U, where for all A, if A is an X, then for all B,
If B is an A.
B is an A if and only if B is in U.
Yeah.
Wouldn't so,
it?
Yeah.
Oh, I was about to say, shouldn't it be if B is in U, then if and only if B is in A? But then that doesn't matter because it's a double pointed arrow.
Yeah, it's the same thing. Yeah, I don't know.
Cool.
Does that seem right to you guys?
Yeah, and then these guys go and become U, pretty much.
But if you take the union of X, wouldn't that be? Wait.
So you're saying if you take the union of X, wouldn't it be like this set, whatever, squiggly, and then A.
Oh, B, C. Yeah, that's what I was thinking too.
Is that what you're saying?
Mm-hmm.
Well, that's not how it's defined in the axiom. So in the axiom, it's talking about the elements of of X.
I think maybe it's because instead of a letter A here, you can instead imagine it as just being wrapped around in a set.
Yeah,
elements
exactly.
inside here.
Mm-hmm. Oh, okay.
So it's not really like a thing of itself, I guess.
Well, like it is, but you can treat it as being just, its elements.
Yeah.
Well, the thing is though, like, isn't like this set just X? Like we don't need to define, because like X is the set of A, B, and C, right? So
yeah,
like this set is just X, right? So we don't need like the union to be in this, because like that basically means like the union is the same as the identity, right? So like that's kind of why it's not ABC. It's the elements of ABC.
Like I think the thing here is you're not for niceness, or for less confusion, I guess try not to think about A, B, and C. Only think of it where the elements of X are just arrays, I guess you could say. The elements of X are arrays. And so you don't actually think of like a single array as being an object in X. It's just like a wrapper. And then you just...
I guess X is kind of like a 2D array. Would that be like the right way to think about it?
I guess. I mean, they don't have to be the same length though, all of the subarrays.
Jagged array or something, but
yeah.
I mean, I guess you could think about it that way, but it's not always useful to think about it that way.
Mm-hmm. As a feels good example, though, I guess it's somewhat useful. It's like you have an array of arrays, and then the union just gets rid of the delimiters.
The inner brackets.
Yeah, essentially. Yeah, functional programming is so nice, or I guess programming as a relationship to math is nice because you can like make relationships.
It's kind of hard to talk about this stuff rigorously when you've been doing it, I guess, naively all this time.
Agreed. All right, next up is Taman explaining the axiom of replacement. It's gonna be fun. Do you want to use the board, or do you think you can do it with words?
I think words will do fine.
Cool.
So, given a set and a function, the image of that set under the function is contained within a larger set. So if you have a function which is just a relation with defined, but it also passes, I guess, vertical line test, but in the set world, as in no input maps to two outputs, and you apply that to a set, then the image of what you get will not be something that, I don't know, falls under Russell's paradox, right? The object you get at the end is still a set in itself.
I have a question on that. So I used to be sort of or not exactly clear on what a function meant. Like I knew what it meant. Like if you have a set here and you have a set here, a function just means that it just, or pretty much, I guess the thing I came up to is that a function, if you have a set and then another set, it won't grow it. Is that accurate to say? Like you can't have one guy here pointing to two guys down here if the function goes down.
Yeah, there's like, because there's a, like the definition of something being functional means like there's a, for every x, there's like a unique y, right? For whatever p of x or
Yeah.
it's defined. So like it just means that like you're just mapping, it's like one to one.
Mm-hmm.
Yeah.
Like in essence, oh yeah.
You could argue that, I guess, the length of the image, or well, the size of the image, well, we're arguing in finite sets now, but the size of the image is always less than or equal to the size of the input set, you could say.
Like I'm sure that's not rigorous, but to me that feels like, or it's a feels good example for what it means to be a function. In the strict like set theory world, where it's like you have a set here and a set here, a function just means that this won't grow.
Yeah.
It will at least stay the same or get shorter.
I prefer to think of that as a consequence of the of like the reason functions were defined the way they were. It's just like the way I think about it, the reason you can't have a function, or the reason like they wanted, the reason like I guess people developing set theory wanted to have something other than a relationship that I guess relates two sets to each other, is because like with, if like one element maps to more than one element, then it's like image isn't, I guess its image is like the set of all the elements it maps to, but if you want to have it, like if you want to just choose one of those elements, it isn't always clear like which one you should choose. And if you do want it to be clear, then you know,
I see.
You it better map to one element.
I see.
I don't know if that makes sense, but
it's like you want to be clear with your maps where like what goes to what.
Not what goes to what, but what to expect as an output. Like if like just think about it from the perspective of programming, right? If your function for like some number has like two potential outputs and you're not sure which one will come out for like one input, then it's not like a very useful, it's probably going to be less useful to you than a function whose input is like, you know, unambiguous, or sorry, a function whose output is unambiguous.
Yeah, I see what you mean. Okay, so that's the primary reason that a function is defined that way. And then
I don't know this. This is just me assuming.
Yeah, because I'm trying to think like if you were using the axiom of replacement, or if you wait a sec. Okay, now I'm confused. Never mind. Okay.
So
can someone explain what the image means, like the image of M under R?
So take your F and then apply it to every single thing in some set A. That's the image of F under A. Well, image of A under F. Stuff. So given a set of all the function, apply it to everything, and the set you get from that is the image.
So it's basically like the set of all possible outputs.
The set of all outputs, not all possible outputs, because I guess that would be more of a range.
Okay.
Like I guess I'll take y equals 1 over x, for example. Your range is all real numbers because all your possible answers will lie in the real numbers, but your actual image is real numbers without 0, because you're never going to get 1 divided by x equals 0.
How about this? If I was doing programming and I had a function called like, is this number odd? And it takes in a number and it outputs a Boolean. The image would be the set containing false, comma, true.
Yeah.
And the input set would be the real number, or I guess, real numbers or something. But no, not real.
Doing that
integers.
Because like you end up mapping to like true or false, right? But like several things can map to the same one, right? Therefore, it's not function.
Some things mapping to the same one just means it's not an injective function, but it's still a function. Yeah.
Okay.
Like the way I think of it is you have the numbers here, and like it just like compresses it, like it gets smaller. And as long as it gets smaller, it's a function. But if you were to do the opposite, where you can put true or false and it gives you out a random number, like that is definitely not a function because it goes from really small to really big.
So one issue with the lecturer's definition of the axiom of replacement is that he's building set theory on top of first order logic, but first order logic does not allow you to quantify over functions.
Mhm.
So you're not allowed to say for all functions f, this holds. Therefore,
Okay.
it technically in ZFC, you for every single function that you have a different axiom of replacement. So there's uncountably many axioms of replacement. We just call them one axiom of replacement. But more accurately, you cannot quantify over functions. Therefore, you need a different rule for every single function.
Oh.
Not
Because
sure.
if you quantify over functions or you quantify over your what they call predicates, then you end up with second order logic, which is stronger, but it also has its own few issues.
I think I maybe understand what you're saying. Let me try to say something and you tell me if what I'm saying is related to what you're saying. So if you have a predicate, P of X, if you quantify that predicate and you put an upside down A, then P of X, what you're essentially saying is P of X0 and P of X1 and P of X2 and P of X3.
No.
And the statement as a whole is a proposition. And so you're saying
No.
no? Okay.
No. Okay. So what you're doing there is you're not quantifying over P, you're quantifying over X, and that's fine. Because if I say P of X, then I say for all X, P of X. The X is the thing that's the variable there. That's totally fine. You
Sure.
can't say for all P of X, because now your P is the variable and P is a proposition. No, well, not proposition, but a predicate. And you're not allowed to quantify over predicates in first order logic.
Okay, yeah. That seems fine, yeah. Cool.
I'm a little confused on this. You said you noted like the difference between the range of a function and the image.
Yes.
What's the difference?
Okay, so let's say I gave you y equals x, right? That's just your identity function over the real numbers. The range of that function is all real numbers. But if I gave you the set 0, like the inclusive range from 0 to 1, the image of that set under my f, or the identity function, is also the set 0, 1. Because you're not going to get all the real numbers, you're just going to get that one restriction that I gave you. So that's the image of that one specific set under the function. Whereas the range is all possible.
So if we go to programming as an example, it'd be kind of like if I had a function that returned, it took in a number and it outputted a number, but I only allow it to enter positive numbers or something. The image is all possible numbers, but the range is all possible numbers. And the image is, again, only positive numbers. Maybe what I said is meaningless. I don't know. Yeah, maybe.
Wait, hold on. Can you explain like that 0 and 1 thing again? So like you said that if you like input 0 and 1.
Okay, so identity function, we're just taking, if I say f, I mean ID. So the range of, and we're going from real numbers to real numbers here. So we're just on a 2D plane, right? So if I gave you all real numbers, then that function f can give me back all real numbers. So that's my entire range of the function. However, the image of a particular set under the function is just what that function returns when it's applied to that set. So if for the set, I gave you the set of every single real number from 0 to 1, I'm going to get back every single real number from 0 to 1. It will not give me back every single real number from negative infinity to positive infinity. Just everything within that one particular range. So that's the image.
Okay, I see.
So would it be correct to say like the image is sort of like the range of a function if a domain is specified on that function? Like if you restrict the domain of it, then
yeah.
Okay, cool. Sick.
All right, that makes sense.
Problem solved. All right, next up, I believe we've gone through the entire list of people, like everybody's gotten a chance to explain. So is it cool if we, yeah, I think 1, 2, 3, 4. Yeah, we've all had a chance to explain. So yeah, I'll go and explain the restricted comprehension. and how it's related to the axiom of replacement. Okay, I came up with a really cool analogy here. Restricted comprehension is a filter function in programming. So you take an array or whatever, and then you just apply a predicate to each of the elements. If the predicate is true, you bring it. It's called replacement. So you bring it to the next set, you replace it. In theory, it's a filter function plus a map function, because you could do something like, say my array here is 1 to 10, 1, 2, 3, 4, 5, 6, and then my predicate will be x squared or something. It's called replacement. In this case, all of them are true, and it's gonna like just bring 1 to 1, 2 to 4, 3 to 9, etc. And that's essentially what restricted comprehension. Oh, yeah, that's comprehension. Then you have universal comprehension and restricted comprehension. And the difference between the two is that restricted comprehension must make the array smaller or of the same size. Like, yeah, I think that's it. Yeah. Because you don't want stuff to blow up pretty much, because that would lead to like whatever, I'm not sure, something illegal probably. So that's the axiom of, or the restricted comprehension, how it comes in. Does anybody have an objection? No.
I don't believe that's quite it. I'm pretty sure the difference between universal and restricted is that from universal, you're just filtering from everything. So I'm saying the set of for all x, px.
Oh, yeah.
Whereas in restricted, I say
you're
for
right.
all x in A.
Okay, I see. Okay, I see.
Yeah.
So here, if I was to continue or to re-explain my analogy, restricted comprehension is where I have a set to begin with, like the numbers 1 to 10, and then I apply a predicate to each of the elements and get a replacement, like the other thing here. Whereas universal comprehension, there is no origin to speak of. I just say P of X, for example, which allows some weird stuff to happen. And so that's why we don't allow it.
Weird stuff being like Russell's paradox. In Russell's
Yes.
paradox, you're not taking anything from anywhere. And that's why
Yeah.
that problem comes up. Whereas if you do Russell's paradox, like that kind of construction, but you have a set that you're pulling from, then you don't end up with a paradox at all.
Okay, cool. So yeah, I think we're good on that. Next up is, oh, this one's pretty cool. Or wait a sec. No, power sets. Let's go with I think, who was the first to explain? I think Avnish, you were the first one after me, of course. Do you want to explain power set?
Sure. But hold on, before that, like, I was a little bit confused about how you like took like, you know, let's say the set is of like 1, 2, 3, 4, right, up to 10. And then you like, you kind of like applied a predicate that mapped like x to x squared. So like 1 to 1, then 2 to 4. Isn't, like, I thought restricted comprehension was just like filtering it. So like instead of you can't change it and then make a new set out of that. I thought it was more like take like the set 1 to 10 and then just like choose the even numbers from it. Is that not what restricted comprehension is?
I think you might be right, yeah. Because I know with universal comprehension, I've definitely done something like x squared, comma, x comes from the real numbers. Like I've definitely done that. Oh, okay, cool.
All right.
Right time in.
Okay, yeah, because like we're doing like, because the notation was like something like y and m such that p of y, right? So you're like basically like you're not changing the elements, you're just like choosing some of them.
Maybe you could do something like this though. You could do x squared, comma, x comes from r, comma, x, like this.
X squared, where
x epsilon.
So x is an element of r, and
R is the real numbers. Yeah.
Okay.
So it's like,
I don't think that's what restricted comprehension is saying though. I think it's just saying like you have like y in like some set M. So like just say y element M, and like the elements of this new set that you're making are the elements from M that satisfy like P of Y or P of X or whatever.
So like, essentially you're saying it's just a filter.
Yeah.
Yeah.
Okay,
Because
cool.
it's like not saying like well, because like you could also like say your p of y was like some function, right? Then you could do that. But like in this case, I think it's just saying like whatever makes that true. Does that make sense?
Mhm.
Like for y element m, p of y, and then you just take all the y in m that satisfies p of y.
Okay, I see. All right. Next one is, or unless there's any more questions. Next one is Axiom of Infinity.
Wait,
Which is really-
we
oh,
didn't
yeah?
talk about the power set.
Oh my god. Oh my god. Yeah, my bad. Yeah, you asked the question. Oh,
Yeah.
okay. Explain the power set. Yeah.
Okay. I think it's like pretty simple, right? So you start with a set, and the power set of that set is basically like all each of the possible subsets. I actually want to try like writing this down in like the formal notation because I feel like it's an easy one to write, and if I don't get it, then I'm probably doing something wrong. So you start with.
Do you want to write it down first? We talk about something different, and then when you've got it all drawn out, you explain stuff that you've drawn.
Yeah. Okay. That sounds a good idea.
Okay. Cool. We can go and move on to the Axiom of Infinity. And Dixon, you can explain this.
So as I understood it, it was basically like if you have a set such that I think it was like you have like an empty set, and also you have something such that this something has let's just say x, right? This x is also contained within other sets. So I think his example was just like the easiest one, or like one of them was just 0. So 0, or sorry, the empty set is just empty set. But also you have like empty set inside an empty set. So you can do this infinite amount of times, and that's an infinity set. And then what he did was like this just maps onto like the natural numbers. So yeah.
Yeah. I have a question. Can't you just do that with the pair set axiom? Empty set, and then empty set with empty set, and then empty set with empty set with it. You can do that just with the pair set axiom. So where does the axiom of infinity come in?
I just think it's like the hardcore like definition for having something go to infinity, because this is just saying for every element inside of like this new set, you like another element in that set is just the set containing that element, so it like goes on like indefinitely.
Okay, so you're saying the axiom of infinity allows you to go on infinitely, pretty much.
Yeah, I mean, because that's what it is by definition, right? Because it's like it contains the empty set, but then it also contains all the elements, or it contains the set that contains every single element. So in this case, it would be like, okay, we know that the empty set is in there, but we also know that it contains as another element the set that contains its elements. So the next one is the set that contains the empty set. And then because of that, that's a new y, that's a new element. So you have the set that contains the new element, and then it like just goes on forever.
I see. I was under the impression that the reason that we need the axiom of infinity is to create the natural numbers. And when I'm saying that, I'm very specific. So you can use the pair set to create the number 0, to create or discover whatever, define, I don't know, the number 0, the number 1, the number 2, the number 3, all the way to infinity, just using the pair set. But the natural numbers, if I was to list off the natural numbers, it's a set, right? If I was to list it off, it'd be 0, 1, 2, 3, 4, 5, etc. That is the natural numbers. Meaning that, and the natural numbers is a set, or is it a set? That's the question, right? We don't know if the set containing 0, 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 infinity, because there's an infinity in there. How come the thing containing that is a set? We don't know that.
Well,
And
we
that's
also
what
don't know that it's. We also don't know that it's not true. Like there's nothing. Like there's nothing about. Like there's nothing that we've learned so far that I guess prevents that from being true. So like, why would you need an axiom for that?
I mean, I'm pretty sure that when it comes to if the natural numbers is a set, like in the lecture, he mentioned that like a corollary to this axiom is the fact that the n is a set, because all you're doing is just taking that like infinite like empty set sequence or whatever and just assigning them like numerical values, right?
Mm-hmm.
Like at the end of the day, it's like it's the same thing, just like different symbols.
So,
I don't know. It's still not clear to me why an axiom is needed.
yeah, or just in general.
Why an axiom is needed to define a set with an infinite number of elements.
Oh, well, so from what I understand, the entire point of having axioms is just to define what, or to expand the definition of a set. And in this case, and we're doing so with like previous knowledge. Like we didn't start off with this stuff. We started with naive, and then we went and defined it rigorously. And in this case, yeah.
Like, is there like, what's an example of like some reasonable assertion that we can't prove without this axiom of infinity? I think that's always like a good like test of how like an axiom, how useful an axiom is.
How about this? The natural numbers are a set, or is a set, I guess. I am telling you, or I think it is the case that you cannot prove that statement to be true without the axiom of infinity, because that's literally what the axiom of infinity is defined as. It tells you that the natural numbers are a set in a roundabout way.
Yeah, like I think for like the union and pair sets, like you can create bigger and bigger sets, but I don't know if like you're allowed to create infinite sets with that.
But if you look at the formal definition, there's nothing about infinity there. It just says that for any element in the set, you can create another element based on that element. And because, and that element will be unique and different from all the elements, all the other elements, and that element will never, like any element that one element creates will never be like another element of the set, because then it would create like a loop. But I don't see where like an assumption is being made here that, you know, that you couldn't like do without. Like if you look at the formal definition, it's just there exists an X where the empty set is an element of X. And for all Y, if Y is an X, then you can create like another, then the like there's like a way to create like another element based on Y, where you take the union of Y and like Y in like a set, Y surrounded by a set, and then yeah, if Y is an X, then Y, like if you, then Y taking the union of Y and Y in the brackets is also an element of X. And so you start with the empty set, and then you have the empty set with the union of the empty set in brackets, and so on and so forth. But maybe I'll just link the Wikipedia article.
Sure, yeah. So I'm trying to think how that, basically the outcome of this axiom is that natural numbers are a set. That is the goal that these theorists came up with when they were trying to come up with this definition. And the way that they were able to say that, I'm not exactly sure with, but somehow they were able to say that the natural numbers are a set. That's the outcome.
Wait, so I guess like, because like the way I wrote it down, and I'm not sure if this is exactly what he said, but I wrote down like, it says that there exists a set that, so there exists a set that contains the empty set, and then for all of the elements in this set, it also contains a set containing those elements, right? So like, let's say we start with this.
Oh, cool.
It also contains the set containing this, right? And now we have two elements. So it also contains the set containing this. So we need to add like, so I think like, isn't that what the axiom of infinity says? Like,
but can't you just get that from the axiom of pairs?
No. I think the axiom of infinity tells you that this thing that Avnish just drew is a set, which we can't know for sure beforehand.
Why can't we know it for sure?
Yeah, why can't we know for sure? That's a good question. I guess that's where we're stuck. Like, because we know from the pair set that this is a set and that this is a set, and we already know that the empty set's a set.
Oh, I guess maybe the very specific part where it comes in is that it allows infinities. Like
that's what I'm thinking. Like,
yeah,
Why
just
can't
tell-
you do that without it though? I don't get it.
Because maybe you're not sure. Like with pair sets, with a pair set axiom, you can only create finite element sets.
How do you know that?
The
It's
pair
like
set
a
axioms.
finite. Like, you know, like for like every time like you invoked like the pair set theorem, like you're doing that finitely many times.
Yeah.
With the
And
same
couldn't you create a construction where it's used infinitely many times?
Yeah, but then you're
here, look, it's just like this definition of like the natural numbers is recursive in a sense, right? Like, couldn't you, like, I don't see why this recursive definition is axiomatic. You're just saying for any element in the set, you can always create another element based on that element. And that's why it's infinite.
Yeah, because
I don't think that's what it's telling you. I think it's telling you that the resulting thing is a set. Like you can do this anyways, but you're not sure if the outcome is a set.
Okay, maybe. Although the axiom of pairs would tell you that it is a set, I think.
So
I see.
I guess this is the this is the axiom of pairs, right? What I just wrote down, which is and the thing is, it's kind of a lot to piece through, but
like what I'm saying is if you apply the axiom of pairs recursively and you say for any element in our set, you can always apply the axiom of pairs again to produce a new element.
Yeah.
I think that would I think that would lead to an infinite set.
I see. How about this? For some reason that I'm not sure, you can only create finite element sets with the pair and the union axiom. For some reason, I'm not sure why, but apparently that's the case, and that's why you need the infinite axiom.
So how do you know that?
I'm saying I'm not sure why, but it must, like, mathematicians have introduced this axiom, so it must be there.
There better be a good reason for it.
Yes, exactly. Yeah.
we want to find the reason though. Should we record a question or something and then send it?
Yeah. Actually. So I did that with Avanisha at our first meeting about this, where we had a question at the end of our hour-long discussion about the first lecture, and we recorded it and I posted it on YouTube. And I don't know, who knows, maybe somebody will comment or whatever. So who wants to, maybe Adar, you want to ask the question? Like, why do we need this?
Wait, before we do,
I'm
not sure
Googling
if
it right now.
I'm not sure that stopping my screen share, if that might erase everything. So do you guys want to talk about this first, which was
the original thing.
Yeah, which is the power sets, I think. Yeah. So wait, crap, now I forgot what this was.
Nice.
Hold on, give me a second. All right, yeah. So basically what I try to do here is try to represent with our notation. And obviously I use the subset symbol here, which I don't know if you can do that, but
yeah,
I don't know. You could expand it if we wanted to in principle. So basically for all M, where M is a set, for if you take any set, what we're saying is there exists a set P of M. So P of M is another set. It's not a predicate. It's a power set. We're calling this the power set.
Okay.
So there exists a set such for all elements of this power set, those elements are subsets of the original M.
Okay, yeah, sure. That works.
Does that make sense? That's basically what I was trying to capture in the whole idea of the set that contains all possible subsets of M.
Yeah, the only thing that I'm questioning is this P of M here, and if it makes sense to put it there. I'm sure you could somehow include it in the big statement on the right here, but overall, to me, it makes sense. This translates into English into the definition of the power set, and I guess that's the entire point of logic, that it just translates into nice English.
Cool. I'm just gonna hold on. Let me just write this down over here real quick, and then I'll stop sharing.
Cool. Yeah, and we could maybe speed through the two last axioms since. Oh yeah, you looked it up and.
So there's basically
Okay.
people who it, to them it's intuitively clear that the natural numbers exist,
Yeah.
and then there's those who reject that they exist. And so having
choose
this
an
axiom is kind of just like a way to, like, because it's useful, like infinity is a
Yeah.
useful concept, is just a way to kind of say, okay, regardless of your opinion, this is the axiom of
Yeah.
our like system, so suck it up.
Yeah,
Literally.
like just in case you don't agree, it's an
Yeah,
axiom.
it's an
You
axiom
can't
now.
argue with an axiom.
Yeah.
Literally. It's just like
Although,
cheating.
The only thing I'm like concerned about though is that axiomatic systems are not supposed to include tautologies, right? So is the axiom like,
Aren't they supposed
right?
to include only Oh, axiomatic systems, like the axioms. Oh,
Right, yeah. So like
see.
if the axiom of
Oh.
infinity can be deduced from the other axioms, then
And it's a tautology.
then
Yeah.
it would need to be removed, right? So that's what I'm
Hey guys, I
concerned
have a fun little trick for you to get 100s in all your classes in university.
about. Oh,
Next
no.
time your teacher asks you to prove something, you tell them, let us define a
Yeah.
foundation of mathematics where P is self-evident.
Yes, exactly. Just like this is it's an axiom. Boom.
It's nothing you can do, bro.
All right.
Literally cheating. But yeah, and I feel that's what the last two axioms literally are. Like in retrospect, mathematicians were like, oh, I want these two things to be true, so I made them true. So
Well,
yeah,
it's more like it's useful for them to be
yeah,
true.
useful.
It's
Yes,
it's kind of like the same thing with definitions, right? Like many definitions seem arbitrary at first, and like yeah, they kind of are arbitrary. Like you could literally define anything to be anything, but the definition, like only the definitions that are actually useful in terms of the like theorems they help you prove are the ones that stick.
Mm-hmm. No, yeah, for sure. So yeah, axiom of choice now. Who has not explained? Let's see.
I haven't done the axiom of,
Yeah.
I haven't like looked into the axiom of choice or the I sort of know what it is, but I haven't looked into it enough. And I also haven't looked into the axiom
Foundation.
of foundation.
Yeah. Okay, yeah. I guess my impression of the axiom of choice is somebody had a problem, and so they introduced an axiom to solve it. And the specific problem they had was to do with was it a basis for vector space? And second thing was complete system of representatives of equivalence relationships. No idea what those two means, but apparently they had problems with those things, and so they introduced this axiom to solve it.
Wait, hold up. So do you think like the fact that they needed to prove that every vector space has a basis is what gave rise to this axiom? Or do you think that one of the things that we need this axiom for is the fact that we need to be able to prove that every vector space is a basis? Like, is it like you kind of made it seem like there were only two problems that they had, and to solve it, they created this axiom? And I'm just wondering, like, was it created just for those two problems? Or did they just like foresee that it would be necessary? So they created it and then it solves way more problems than just the vector space thing.
There's probably more problems, but I think those were the only two that he
Yeah.
mentioned in the lecture. But I'm pretty sure this is like, so this axiom is like completely independent from the rest. So there are like some mathematicians who don't even like agree with this axiom. So you can
There's a
either-
good
Yeah,
reason why
true.
they don't.
Like-
Yeah.
So
Yeah.
basically, like one consequence of the axiom of choice is that is something called like the well-ordering theorem, which basically states that for any like well-ordered set, for any set, you could define an order relation on it such that it is well-ordered. And what well-ordered means is that it has a smallest number or like a smallest element. So for example, like subsets of the integers are well-ordered, right?
Yeah.
But there's always going to be a smallest integer in a finite subset, right? But when you get to something like the real numbers, where you have like something like this, like an interval like that, where you don't go all the way to zero, but get close. The well-ordering theorem states that even for this set, you could also, does everyone know what I mean when I say like an order relation?
I don't, but your explanation seemed pretty clear.
Yeah.
So like an order relation it's like, we could go over it formally, but all you need to really know about it is just a way to like say this is greater than this. And you could define like what is greater in a number of ways.
Yeah.
Right? Like you could say like you could, for example, you could order people by height or like, I don't know, like weight or whatever. Like there's multiple ways to order stuff. And so, I mean, like order relations can get more like exotic than that, but you hopefully get the point. There's a way to order things or to order any set such that it has a smaller element, even something like that, like that interval. So yeah, that's why people like, you know, that's why some people don't agree that the axiom of choice should be a thing.
Yeah, basically it just brings some nasty consequences. And so
but it's
like,
also supposed to be useful. So
yeah, it's like good and bad. Oh well, what can you do? And final one on the Axiom F Foundation. Yeah. Does anybody want to talk about this?
I mean, not a lot to cover. It's just saying that like a set can't contain itself.
Yeah, essentially.
Otherwise.
Like that's what I got from it too.
Yeah.
it also said that a set, like for any set that isn't empty, there has to be an element in that set such that the union of that element and the set is
Intersection.
like the empty set. Oh, sorry,
Intersection.
the intersection. Yeah, the intersection is empty. Which, yeah, like to me that doesn't seem super intuitive, because like
it's a roundabout. From what I understand, it's just a roundabout way of saying. Like mathematicians they like short definitions, I think, and so they'll have some really weird definition that if you like whatever develop it, eventually it will say no set contains itself. In this specific case, if a set did contain itself, then the intersection between that set and any other set in the set would not be empty. Trying to think of why, but apparently it's not empty.
Okay.
Why would it not be empty? Oh, because it's a set containing itself. So that set will have the other person's set. Like if it's a set containing itself and you're trying to intersect it with something here, then this something here and on the inside of this guy, they'll be the same here. And so the intersection will find something in common, which is illegal according to the big thing at the top. Like the thing at the top tells you if you take the intersection between two of the sets inside this big set, it needs to be empty. But if the small, or if one of these guys is the big guy, then the big guy contains the small guy. And so when you take the intersection between the two, you're going to get something. It won't be empty, which breaks the proposition or the axiom.
I don't know. I'm gonna have to think about it a little bit.
Yeah, this is, yeah, we're gonna have to think about it. In any case, yeah, I think we've gone over everything. Yeah, next week is really cool because now that we have the natural numbers, what happens is we find a way to build the integers, which includes negative numbers, and then using the integers, you build fractions, and then using fractions, you build real numbers. That's basically the entire point.
Yeah, it's actually pretty cool how you construct real numbers from the rationals.
Yeah.
There's like multiple ways to do it, but the way I know is called, I don't know how to pronounce it. It's like D-kind cuts or something.
Oh, yeah. Something like that. In any case, oh, and I just got, or not just got, but I got an email from Frederick a few minutes ago, and he said he wasn't able to make it, but let's do one the following week.
Okay,
so
sweet.
Yeah, next week he'll be here. All right, we're good.
All right, cool.
Next time.
Sorry?
Maybe we can ask him like all the questions.
Yes, all of these things. Yeah. For sure. All right, well, see you guys next week.
Awesome.
Cool.
See ya.
Bye.